So like we talked about yesterday in our video, the pH scale or the pH of a substance is based, again, exclusively on the hydrogen ion concentration. If you're using the pOH scale, obviously it's based on the hydroxide ion concentration. Okay, and so when you're solving problems that involve pH, you have to know the hydrogen ion concentration. Now yesterday, in the previous video I should say, the hydrogen ion concentration was easy to find because we use strong acids and strong bases. Okay. However, with a weak acid, the concentration of the acid is not the hydrogen ion concentration. Okay, we've learned that when in our first part of Unit 6, when we were dealing with the equilibrium constant and using the equilibrium constant to find the concentration of the products. If you have a weak acid, HA, and it's in equilibrium with H plus and A minus, and the concentration of HA is, 0.125 molar, let's say, that does not mean that the hydrogen ion concentration is 0.125 molar. In fact, it's not 0.125 molar. It's way, way less than that, okay, because it's a weak acid in an equilibrium system. Okay, with strong acids, absolutely yes. And again, there's no equilibrium arrow. If this is 0.125 molar, then so's the hydrogen ion concentration. But when it's not a strong acid, it's an equilibrium system, and they don't end up at the same point. So, what do you have to do? Well, go back to the first part of Unit 6. You have to make an ice table. Okay, so let's look at these couple of examples. HCN has an equilibrium constant of 6.2 times 10 to the minus 10th. Write the chemical equation for the dissociation of HCN and water. And then they want to know, what is the pH of a 0.25 molar HCN solution? So first of all, our reaction is HCN is going to be in equilibrium with, and what does every weak acid do? It donates a hydrogen. So you always know what a weak acid's going to do. It's going to lose one of those hydrogens, and then whatever's left is going to have that negative charge up in the corner. So it's H plus Cn minus. Now, we're going to do an ice table here a couple times, but hopefully you're going to get to the point where you don't need it anymore with problems like these. So you've got a 0.25 molar HCN solution. So that's initially 0.25. This is 0. This is 0. Now, this is going to become pretty common here. This is going to go down by x. These both go up by x, just like we saw in the first part of Unit 6. And then we have 0.25 minus x. Okay, and again, we can make that assumption that x is going to be a really, really small number, which it is. So we can say 6.2 times 10 to the minus 10th is going to equal x squared over 0.25. Now, and again, I made that assumption that 0.25 minus x is roughly equal to just 0.25 and replace that in there. Okay, and remember, guys, we're trying to find the pH of the solution. To find the pH of the solution, we have to have the hydrogen ion concentration, which is equal to x. So we're trying to solve for x here. So now I need to take, now it's to the calculator part. I'm going to take 6.2 times 10 to the minus 10th. I'm going to multiply by 0.25, and then I'm going to take the square root of that. And I get an answer of, and again, look at how small x is. That assumption is certainly valid. 1.24 times 10 to the minus 5th. Okay, and that is the x value. That is equal to the hydrogen ion concentration. And so now to get the pH, just like how we learned earlier, now we can take the negative log of that answer, and that will give us our pH value. The pH is equal to 4.90. Okay? And that's it. That's what you've got to be able to do with weak acid solutions. Okay? Now, we can also go backwards. Okay? In example 2, they give us the pH. So the pH of a 0.1 molar solution of acetic acid is 2.87. So if the pH equals 2.87, that means, and again, think about the overall equation here. If this is the acid then the equation is going to be HC2H3O2 in equilibrium with what happened with HCN. Same thing is going to happen here. You're going to get the H plus. This comes off, and you're left with this. Okay? So if the pH is 2.87, I'm going to take 10 to the negative, oops, 10 to the power of negative 2.87, and that gives me, so that tells me the hydrogen ion concentration is equal to 1.35 times 10 to the minus third. Okay? Now, if the hydrogen ion concentration is equal to 1.35 times 10 to the minus third, and for every one hydrogen we get the same amount of acetate. Remember here, the hydrogen ion concentration was X, so was Cn minus. So if the hydrogen ion is 1.35 times 10 to the minus third, then so is the acetate ion. Which means, again, let me draw it a little bit better than this. Let me give myself a little bit of room. So if we were to make an ice table here, H plus C2H3O2 minus ICE. That means that at equilibrium, the hydrogen ion concentration is 1.35 times 10 to the minus third. What was it initially? 0. So it went up by this. And again, that's our X value, which means, again, here, Cn minus, which means here, the acetate ion is going to go up by the same amount. So those are equal to each other. And normally, in this case, remember here, when it was a minus X, we said, it's going to be a small number, just take the X out. We did that to avoid having to use the quadratic equation. If we know that the concentration of the solution is 0.1 molar, 0.1, and we know that these are going up by 1.35 times 10 to the minus third, there's no need to say, forget that part. We can say, well, this is going to go down by 1.35 times 10 to the minus third. So I'm going to take 0.1 and subtract 1.35 times 10 to the minus third, and I get 0.09865. Okay, and it's not much different, but again, the only reason we take out this minus x here is because we don't have to do the quadratic equation. We're not doing the quadratic equation here anyway. We're simply trying to find the equilibrium constant. Okay, because now that we have all our equilibrium values, now we can plug it into the equilibrium constant expression. So K is going to equal 1.35 times 10 to the minus third, and it's H plus and C2H3O2 minus, so I'm just going to square it because it's the same number, over 0.09865. And yes, if you leave that answer as 0.1, they will mark it wrong on the AP test. Okay, so 1.35 times 10 to the minus third squared divided by 0.09865 equals an equilibrium constant value of 1.85 times 10 to the minus fifth. Okay, and that is our equilibrium constant. So you can use an ice table to find the pH of a weak acid or weak base solution, or you can use the pH to work backwards to get the equilibrium constant, okay? Obviously, in example number 1 up here, they gave us the equilibrium constant. In example 2, they asked us to determine the equilibrium constant. So either way, we were using the pH to find the hydrogen ion concentration to either find the pH of the solution or use the pH of the solution to find the equilibrium constant. Okay, now one last thing here. Notice that, for example, here, that the pH was 2.87 and that the hydrogen ion concentration was to the minus 3. Okay, and up here, the hydrogen ion concentration was to the negative fifth, and the pH was 4.9. Okay? A lot of times on multiple choice questions, you will be asked to approximate the pH based on the hydrogen ion concentration. Okay? So, when the hydrogen ion concentration is 1 times 10 to the negative whatever number, then the pH is equal to exactly N. For example, if the hydrogen ion concentration is 1 times 10 to the minus second, then the pH is 2. If the hydrogen ion concentration is 1 times 10 to the minus 8, then the pH is 8. Okay, anytime it's 1 times 10 to the negative whatever number, that's what the pH is. Okay? If the pH is equal to exactly 3, then the hydrogen ion concentration is 1 times 10 to the minus third. If the pH is 7, then the hydrogen ion concentration is 1 times 10 to the minus seventh. If the pH is 0, then the hydrogen ion concentration is equal to 1 times 10 to the 0, which is just 1. Okay? Now, but when the hydrogen ion concentration is any number other than 1, such as 2.5 or 3.6 or 8.7, anything time it's not a 1, then the pH is between N minus 1 and N. So whatever this number is up in the corner, the pH, can approximate it to, let's say it's 5, 2.5 times 10 to the minus fifth. Then the pH must be between 4 and 5. Okay? If it's 3.6 times 10 to the minus eighth, then the pH must be between 7 and 8. Okay? If the hydrogen ion concentration is 8.6 times 10 to the minus third, then you know, simply by looking at this number right here, that the pH must be between 2 and 3. If the hydrogen ion concentration is 6.2 times 10 to the minus fifth, then the pH must be between 4 and 5. Okay, so use that number up in the corner. It's between that number and one number less than it. Okay, so if the solution has a hydroxide ion concentration of 4.2 times 10 to the minus fourth, that means not the pH, you can do it with POH as well, that the POH is therefore between, again, 3 and 4, which means the pH is therefore between, remember, how do you go from pH to POH? You take 14 minus the POH. So 14 minus 4 is 10, 14 minus 3 is 11. So the pH therefore must be between 10 and 11. And remember, anytime it's greater than 7, it's basic. Okay, one more example, then we'll stop. Okay, a 0.50 molar solution of a weak acid, HA, has a pH of 3. Without a calculator, determine the equilibrium constant. Ugh, gross, without a calculator. So again, if the pH is equal to exactly 3, that tells us right away that the hydrogen ion concentration, and remember, it's a weak acid, so it's HA in equilibrium with H plus and A minus. It means the hydrogen ion concentration and the A minus concentration are both equal to 1 times 10 to the minus third. Okay, so that means when we calculate the equilibrium constant, we're going to have K equal to 1 times 10 to the minus third squared. Okay, because think about that ice table. I'm kind of skipping the ice table part just to save some time. But in the ice table, these would both be equal to 1 times 10 to the minus third. So we square them over 0.50. Okay, and 1 times 10 to the minus third squared is 1 times 10 to the minus 6. And anytime you divide by 0.5, that's the same thing as multiplying by 2. So that just becomes 2 times 10 to the minus 6. Okay? And so that is how you deal with pH when you have a weak acid or a weak base.